We're now going to look at the way that enolates can have more than one regioisomer when they are formed from ketones. Aldehydes have only one alpha carbon. Therefore, they will only form one possible enolate. However, unsymmetric ketones can form two possible regioisomeric enolates. For example, if we look at butane 2-one, we can deprotonate on either carbon 1 or carbon 3. Both of these are alpha carbons. We will call carbon 1 alpha 1, and we will call carbon 3 alpha 2. If we deprotonate on alpha 1, using a base to remove a hydrogen from alpha 1, we would form this enolate. If we deprotonate from alpha 2, using a base to remove this hydrogen on alpha 2, we would form this enolate. It turns out that we can control which enolate is formed preferentially by controlling the conditions of the deprotonation. The less substituted enolate would be formed faster because there would be less steric hindrance to removing the hydrogen on alpha 1 than there would be to removing the hydrogen on alpha 2. Because there's less steric hindrance, collisions would occur more often, and deprotonation would occur generally much faster. Therefore, if we had 100 of these and we allowed them to react, we would see that we would get initially a much larger percentage of this enolate formed from the less substituted alpha than we would of this enolate formed from the more substituted alpha. Organic chemists call the faster formed enolate the kinetic enolate. If we recall, the area of chemistry that studies the rates of the reactions is called kinetic. In contrast, the more substituted enolate would be more stable. The reason for this can be seen if we look at the resonance structures. When alpha 1 is deprotonated and we do resonance, we get an enolate where the double bond is essentially monosubstituted. You recall that monosubstituted double bonds have a higher potential energy and are therefore less stable. In contrast, if we look at deprotonating at alpha 2, the enolate would form a resonance structure in which the double bond is disubstituted. Disubstituted alkenes are more stable. They have a lower potential energy. So therefore, we would expect that this enolate overall should be more stable. The more stable enolate is called the thermodynamic enolate because the area of chemistry that studies energy changes and stability is called thermodynamics. To get mainly the kinetic enolate, we need to use fast, irreversible conditions that limit the ability for the enolate to equilibrate. We get these by using a slight excess of very strong base and a low temperature, and then we add the electrophile soon after we form the enolate. Why does this work? The kinetic product is formed faster. Once it is formed, the product is trapped as the kinetic product because the reaction won't go in the reverse direction under these very cold temperatures. So if we imagine, again, having 100 of these react, we would form a much larger amount of the kinetic enolate, and it would essentially stay trapped as the kinetic enolate because the reverse reaction going back to the original ketone would be very slow, and therefore there would be no opportunity for the alpha 2 carbon, the more substituted, to be deprotonated. Because reverse reaction is slow, there's no chance to try again to form the other enolate. If we react the enolate with an electrophile, we can also get products from the kinetic enolate when we use a weak base, but have the electrophile already present. In this case, the rapidly formed kinetic enolate will react with the electrophile again before the enolate has a chance to equilibrate. To get mainly the thermodynamic enolate, we use slow, reversible equilibrium conditions. We can get these by using slightly less than one equivalent of a base, or by using a relatively weak base, by applying a warm temperature, and by giving it time, usually 30 minutes, to equilibrate before adding the electrophile to complete our desired reaction. The diagram below shows how this would give the thermodynamic enolate. Again, if we had 100 of these ketone reactants, we would see that the kinetic enolate is formed initially in a much higher amount because it's formed faster. However, if we have this at warm enough temperatures, the kinetic enolate can react either with the conjugate base or with, if we haven't used a complete equivalent, with one of the ketones to protonate again and become the ketone again. This then gives us another opportunity to deprotonate, possibly on alpha 2 instead of alpha 1. When one of these is deprotonated on alpha 2, it will become the thermodynamic enolate. The thermodynamic enolate is much more stable than the kinetic, so the activation energy to go in the reverse direction is much higher. Therefore, the reverse reaction from the thermodynamic enolate is much slower. Therefore, what we see is a situation where we rapidly form the kinetic enolate, but then it begins to equilibrate backwards. We get significant amounts of the ketone formed again. Then every once in a while, one molecule of the ketone will go to the thermodynamic and get stuck there. So then we have fewer molecules in this equilibrium. Again, another one goes here, gets stuck. And so it's a Chatelier principle thing. As we pull more and more molecules down into this product, eventually we will have mostly thermodynamic enolate and very little kinetic enolate. We're going to see reactions where we form enolates and then allow them to react with other species in order to get a variety of products. The specific conditions and the resulting enolate that we will get are summarized below. If we want the kinetic enolate, we will use very strong base, greater than one equivalent at very low temperatures. An example of this would be lithium diisopropyl amide, 1.02 equivalents at minus 78 degrees. We're going to discuss this reagent in a later reaction. To get the thermodynamic enolate, we could use very strong base, but less than one equivalent at a higher temperature. So for example, again, lithium diisopropyl amide at 0.98 equivalents at 0 degrees C. Or we can use what we termed a strong base, something like hydroxide, greater than one equivalent, and an even higher temperature like room temperature. Some examples would be sodium hydroxide in ethanol or potassium T-butoxide in THF.